So in 512, the only thing I need you to know for that little section, I would like you to read it just so you kind of have an understanding, but what I need you to know is anomalous configuration just means that it doesn't follow the rules that we've been talking about and the rules that we're going to use for writing these. So it doesn't exactly look like we would predict it to look like. The reason it doesn't look like that is based on where it is and what little arrows we're drawing for it. The off-ball principle, which remember is telling you to fill the lower energy levels up. Sometimes an electron will go into a different orbital just so that it could be lower energy in its configuration. So if you read the paragraph, you kind of see why it's because of off-ball, but it's a really short section and it just sort of tells you why there's different electron configurations. So if I ask that question, it would just be kind of like a multiple choice question. So all you would need to know, and you can come back and watch the video, is that the anomalous configurations are because of it trying to fill the lowest energy level orbitals first. Okay, getting into 513, we're going to talk about trends in electron configuration, and in order for me to get in the trends, I want to write a couple of the electron configurations again. We're just going to write the noble gas ones. So you saw the noble gas ones in the previous video, but we can actually write a noble gas form of the orbital filling diagram, which is the one that has the little arrows to it. So before I talk about the trends, and before we do these, there's this kind of shortcut that you can see that helps you realize how quickly you can write these noble gas electron configurations. The way I showed last time was kind of longer, but I wanted you to understand why that's true. Okay, there's these blocks on the periodic table. So if you look up here at this slide, so this is, if you want to go print this out really quick, so why don't you pause the video and go print out slide 55 and go print out slide 56. So pause the video, do that. If you don't have like a printer or you don't want to use your printer ink, just have those up and available on your computer screen so that you could look at them when I'm talking about them. Okay, so if you have those in front of you, I only put up slide 55 because I don't have enough room. But in slide 55, you'll see what's also in 56. So see how it's color coded? So these colors are showing you the blocks, and we call them blocks because they're kind of blocked off for each one of these S, P, D, and F. So when we write out these configurations, like some of the electrons are in S, some of them are in P or D, or we won't get to F, so I'll leave those out because it's a little more than we need to do right now. So these first two, maybe we'll even write it up here. These first two are S block, and then these and this orange range are the D block, and then over here, minus the helium because this actually goes over there. It's placed over here for other reasons because it's a noble gas. So this is the P block, and then this whole thing here is the F block. So when you write out the electron configurations, instead of having to like go through that pattern and read through all of them, when we get lower on the periodic table, it'll be easier if, when you go to sodium, so let's just go to sodium over here and kind of mark it so we can see that all these are going to be the same. So we have sodium. And it has 11 electrons, which is what we used before. But this time what's going to be important is, since we used the noble gas electron configuration, remember you go back to the previous noble gas, so the one before it has to be the one before it. So the one before it is neon. Then when we add on to that, you know this is the S block because of here. So you're counting, so we're period, remember periods are the rows, we're period 1, 2, 3. So it's period 3, which corresponds to the N value for S's and P's. And then it's in the S block. And it's the first one in that S block. So that's it for sodium. So now the pattern for potassium. So notice that potassium is still in the same column. So group 1A. So if you go to potassium, and you might want to just pause the video for a second and try to write the potassiums one, and then you can see if you're getting it. Okay, so for potassium, the noble gas before the potassium is argon. And again, we just put that in little brackets. You have to put it in the brackets. So we have argon. And if you look at argon and you come back to potassium, it's 1, 2, 3, 4 periods down. So that means it's a 4. That's still in the S block, right? The S block. And it's still the first one in the S block. So when you kind of notice a pattern here, when you have this noble gas electron configuration, you're seeing what's on the outside. So you could see that the outside electrons in the highest principal energy level, there's only one of them. That tells you how many valence electrons you have for each one of those particular elements. That's going to be important, and this is what you're doing in lab this week, is counting up the valence electrons so you can draw those Lewis diagrams with the dots for the lab. Okay, noble gas orbital filling diagram. This is useful because it sort of really condenses what you're going to have to do when you draw the little arrows for the orbital filling. So we know, we can just look at this. So now for sodium, so we're just going across, we're still on sodium, still has the same noble gas before it. Remember for these, we're just writing what the orbital is that it's in. And then the little arrows represent the electrons, and we only have one in this 3s orbital. And then we go down to potassium. So if you want, you can pause it for a second and draw the orbital filling diagram. So for potassium, put argon in the parentheses things, and then orbital filling diagram has the line for the orbital. It's a 4s, and there's one electron. So what is significant for the chemistry is there's one electron in the outer shell. The outer shell is what the valences are. And that one electron is what we call spin up. So there's one unpaired electron in the orbital. And that, again, gives way to the chemistry of it. So so we did some over here in the S block. Let's do some over here in the P block. So we'll do the same kind of thing. If you want, when I write up each one of these elements, you can pause it and try to write out what we wrote out before, because it's the same kind of pattern. So let's do chlorine, and again, we'll stick with the same group, because there's a pattern when they're in the same group together. So the noble gas for chlorine, so let's put this as a different highlighted color. So we have chlorine. So chlorine, if you go back to the last noble gas, it's neon. Now we got to go across to chlorine. So this is 1, 2, 3. So third period. And we got to go all the way over to it. So this is the S block. So we're going to fill up the S block, because we got to fill it up and get all the way over there. So we fill up the S's. And then we're still in period 3. And we got to continue. So now we're continuing into what is the P block. We're still in period 3. And in the P block, we go over 1, 2, 3, 4, 5 places. So then when you do bromine, so I would pause it and do bromine. Think about for bromine, and let's highlight that. Think about for bromine that you're going to have to go through this middle part, which is the D block. For the D block, the number that's in front of the D, just like these numbers, is 1 less than the period number. So for bromine, we go back to the last noble gas, argon. And then we start filling in. So for S, it's going to be the same, period 1, 2, 3, 4. So we know we go down 4. We fill in our S's, because we're going all the way over here. So then, when you go from the S, you're moving into the D block. And you have to show that you're going through the D block. The D block is always going to be 1 less and it's N. We're filling up the D block. So if you go and you count across that D block, I'm not going to count across it, but there's 10 across here. So we're going across 10. Then we end up in the P block again. And the P block is still the 4th period down. So it's 4. And then we count across 1, 2, 3, 4, 5. So 4P5. This is going to be a little different in terms of valence electrons. So valence electrons for these, I'm going to kind of run out of room, but the valence electrons for these are the ones that are in the highest N. Both of these are the highest N. So these 7 electrons exist in the highest principal energy level N. So those have a total of 7 valence electrons. This has a total of 7 valence electrons as well. Seems like it would have more because you're reading all the way across, but it's only these 2 that are the highest N, and it's these 7 total that are in that. So then really quickly, let's do the noble gas, because this is kind of good practice. Orbital filling. I'm just going to put my little noble gases here. Think about that you have to have your 3s and your 3p, and remember p has 3 orbitals in it. And then for each one of those, you have to put in your electrons, one up, one down. When you fill the p, whose rule is it that tells me I gotta go across one at a time? So that's Hund's rule. So if you look, this has the 7 valence electrons. And so sometimes they'll put it in this order when we get down here, but when I put these, I'm just gonna put them in that same order that they are instead of grouping the highest principal energy level. So sometimes they'll put the 3D before the 4s just to group together what's going to be the valence electrons. So really quick, so 4s, 3d, if you look back at D on that chart that summarizes all of these, how many orbitals are in an S, a P, a D, or an F, you would look at D and see that it has 5 orbitals in it, which means you can put 10 electrons in it. So again, I'm filling them one at a time. So you think about what rule that is making me fill them one at a time. So that's Hund's rule. So I fill up the D, because the D is full with its 10. And then the 4P has 5 electrons in it. So I filled up that, except for this last one that has the unpaired electron. So remember that each one of these atoms that we did, whether it's the sodium, potassium, or it's these two, they tend to form ions. So in the next part, I'm going to put these up as their neutral atoms. I'll leave this part up, so you might want to write that again. And then I'm going to show why those particular ions form. So I'm kind of skipping ahead to section 6.1 because it goes along with what I was just talking about. And that's why I grouped a couple of the chapters 6 ones in this week, because especially 6.2 is really straightforward. It's just sort of looking at patterns that you can look up anyway. So 6.1 needs some explanation because this explains why ions form. So ions form, if you remember, to make the atom more stable. And for us, stability in terms of valence electrons is some magic number. So the magic number, remember, is 8. That's why the noble gases all the way over here in group 8A, which means they have 8 valence electrons, are the stable ones. They were called noble because they're stable. So if we come back, and this is what we had on the slide, not slide, but on the board before, I just rewrote it, is the noble gas electron configurations for each one of these. I want to point out really quick here in the, if you can see the color purple. So right here, sometimes, so if you're looking online at other videos, or maybe even Alex homework does this, it doesn't matter that you put them in that order, like you're filling up based on the off-ball principle. But if you want to see it with the highest energy level, not highest energy level, but the ones that are valence, the ones that are on the outside in the highest principal energy level, you can order them that way. So you could put like them based on these n numbers. So like n equals 3, and then these are n equals 4. So you can just look at that pattern. So coming over here, we talked about these both have 7 valence electrons, and again, it's easier to see here because that's the highest principal energy level. 7 valence electrons. These both have 1 valence electron because in their highest principal energy level, they only have 1 electron. And then notice, even though we had said this like a long time ago, whatever the group number is, if it's an A group. So I put up here the ions formed based on the A group. Those are the ones that have this like specific pattern to them. Valence electrons is going to be the same as the group number. So if I do the chloride ion forms, because if it has 7 valence electrons and it wants 8, it needs to gain an electron, which is why it goes from the neutral chlorine over to the chloride ion. If we add an electron to make it more stable, we show that in the electron configuration. So now that P shell is full, it has 8 valence electrons, which is stability. If you look here, it's the same thing. That extra electron got added into the P shell to make it full because that's more stable. Down here for the ones that lose 1 electron, and remember they lose 1 because it's easier to lose 1 than to gain 7 more to have 8 valence electrons. They end up losing that 1 valence electron and having the same configuration as a noble gas. And we know the noble gas is stable, and these noble gases have 8 valence electrons. So they try to show this general pattern down here, and there's a table that looks like this, and I wanted to show you because the table is useful, but it's sort of not understandable at first. If you look at the 7 A's, for the pattern that they have, remember N is the same as these numbers. So for the 7 A's, they're going to have, for their valence electrons only, some N value that's the same. And then they're going to have 7 total because they're all going to have 2 in the S and 5 in the P. Then the 1A's, it's even more obvious for the 1A's. For the 1A's, which both of these are, they're going to have N, whatever that N value is, and then they're all going to have 1 valence electron or 1 electron in the S. So both of these have different N's, but they're in the same subshell S with 1 electron in them. So see how N could be like 3, 4, we go down to 5, 6, 7. So when you go through those, you're showing different N values, but for that column, 1A, all of them may have a different principal quantum number, but that subshell that exists in, that electron exists in, is always going to be an S. So I didn't cover 2 sections because you can really just read them and see the trend, and I'm not going to go too much into the theory behind it. Section 514 gives the trends for atomic radii, and section 6.2 gives the trends for ionic radii. So I just want you to go through and read the book and look at the examples for those. Those don't really need videos associated with them.